All right, welcome to my lecture on estimation. There are two main methods that we'll use for estimation. So one method is the method of moments. And the other method is the maximum likelihood. Okay, and this one's very important. Okay, but we will discuss both. Okay, so method of moments. So the first is to let x1 through xn be data. Okay, and the second is to set e of x to the k equal to the summation of x sub I to the kth power from I equals 1 to n divided by n, and solve for the parameter of interest. Okay, and one interesting thing is this k here. Typically, k equals 1 or 2. Sometimes both. Okay. Now let's do the maximum likelihood estimate. So it starts off the same. Let x1 through x sub n be data. Second, form the likelihood function. This is going to be the product from I equals 1 to n of f of x sub I comma theta. And now here's an optional step. I'm going to call this L of theta. Form the log, the likelihood, little l of theta. Okay. Now, third is to maximize L of theta or little l of theta. They're equivalent. Okay. And then the last step here is to solve for theta. That, when you solve for theta, that's your estimate. As a function of x1 through xn, your data. Okay, now we're ready to see this in action. So let's do a quick example. let's estimate the parameter beta of the exponential distribution. From the data x1 through xn. So this is step 1 in each case. So by the way, the exponential distribution right here means this. F of x is going to be 1 over beta times e to the minus x over beta for x greater than 0. Okay. So let's do the method of moments. So the second step, because we've already done the first, is just to calculate e of x and set this equal to the summation of xi from I equals 1 to n divided by n. Well, this piece right here, that's beta because it's an exponential distribution. And you can see page 78 if you like. So beta is going to be equal to x bar, and we solve for beta. So once we solve for beta, our third step is going to be beta hat is equal to x bar. This is our estimate. Beta is just the average value. Okay. Okay. MLE method. And MLE stands for maximum likelihood. Okay. So the second step, because we've already done the first, is to form L of theta, which is going to be f of x1, comma, and by the way, theta is equal to beta in this instance. And we know these density functions. These are the density function of exponential beta. And that density function is going to be 1 over beta times e to the minus x over beta. And that's x sub 1 times 1 over beta times e to the minus x sub 2 over beta times 1 over beta times e to the minus x sub n over beta. Now, just using rules of exponents, this is going to be 1 over beta to the n times e to the minus summation of xi over beta. And that sum is from I equals 1 to n. Okay. Now I'm going to form L of beta, which is the log of L of beta. So I'm going to take the natural logarithm of that previous term we just had. So that's going to be equal to the log of 1 over beta to the n times e to the minus summation of xi over beta. Now, using properties of logs, this is going to be minus n times the log of beta minus the summation of xi over beta. Now, we're on to our third step, maximize L of beta. And I can maximize the log of beta just by taking its derivative and setting it equal to 0. After all, that's what Calculus 1 says to do. So I'm going to do L prime of beta, so minus n over beta plus the summation of xi over beta squared. Remember, my variable is beta, so I differentiate with respect to beta, not x. Now, we're going to proceed by solving for beta. So this is going to be minus n times beta squared plus n times beta squared over beta plus the summation of xi over n is equal to 0. So now, there's no n there. If we go back, we can see it's just summation of xi. So we're going to have minus n times beta equals minus summation of xi, divide by n. So our last step is that our estimate beta hat is going to be x bar. In this case, it's the same as method of moments. But that's not always going to be the case. Okay. True. Always. Okay, so that was our example of estimation for the exponential distribution. We'll try a few more next time.